Hey there.
Hello.
Hey, just checking the other meeting. I thought you might have gone in there.
Oh,
Because usually you're right on time. Anyways, how you doing?
yeah. I'm good. How are you?
Pretty good. How's it going in class and everything?
It's good. Yeah.
Good. Okay, just got your email. How'd that go last week? Your thing,
It was good.
quiz or test? I forget which one.
Quiz. Yeah.
Quiz, yeah. Good. You got a good score?
Yes.
Nice. Good. All right. Get started. We got conservation of momentum. Pretty much the same. I wonder. Here we go. We're talking about elastic collisions. I was mentioning that before. I just realized, do you see how important it is to like go through this entire process and say, okay, stop. M1 equals 1325. Because like, because now is when it matters. Because if you didn't have that down, now you'd be like so lost. And 20.00 m per s, what is that? And you know very well it's velocity. Okay, draw your picture right away, so I'm glad that you got there. All right, so conservation momentum, we know, again, it's always, can you see this? Is it all right?
Yes.
That's what it means. And there's a situation, and we're talking about the momentum of the system now. So the first thing, honestly, for momentum, well, we know it's conservation of momentum. That's what it means. As always, of course, P equals mv, but we got to be a lot better than that by now. So we got to say I and F. Oh, in fact, is this how your instructor does it? Because I want to do it as closely as possible. This is how I do it, but do they kind of like, there's an initial situation and a final situation. That's the point, right?
Mm-hmm.
Okay, so first thing is that we have a car traveling and a truck traveling. So the first thing, perfectly elastic, and the car is propelled to a new velocity. Okay, so the car is moving. We can say, I don't care if you want a box or a point, it's a point actually, but same old stuff, that's always true. This is the car, we'll say car. And we say 20 meters per second, 20, or whatever. And the truck, make a longer box or just another point, doesn't matter. It rear ends the car. So we have a velocity of the truck. This is what you want to do here. Again, I'm looking at this situation. This is the initial situation, and I'm going to calculate the initial momentum. And I'm going to calculate the momentum, not just of the car and not just of the truck. We call it a system, the whole thing. This is a system, the car and the truck. Okay. We'll get right into that once I finish this truck. That's literally what's happening just before the truck hasn't hit the car, and all of these things are true. We got a mass, fine. We got two velocities, but then go ahead and say, oh, what happens? It got hit. We don't know how fast the truck is going. Doesn't tell us. Well, we now know the car is going faster. 28.5. Take note of the final situation. Initial, again, the system is this whole thing. That's what I wanted to say earlier. When it's conservation of momentum, it's not like the momentum of the car is conserved. No, wrong. The momentum of the truck or whatever. No, the momentum of the system. What is the system? Well, it's the total momentum. That's the most important point here. I think I want to go to a new page. But the momentum of the system, what is that? Well, it's the momentum of the truck plus the momentum of the car. What is that? P truck plus P car. Initially. That's the system. Okay, I should get to the questions. How fast will the truck travel after the collision? There you go. So let's get it in there. Did you write this down? Do you want to write it down? Okay, you got it. Question mark for the truck. That's the first thing I want to know. Guess what? That makes a lot of sense because that's the easiest thing to find. Why? Because we have this. conservation of momentum. What is the total momentum initially of the system? Like I said, it's the truck and the car. Well, that means that PI, the left-hand side of my equation, is the initial mass of the truck
Mhm.
times the velocity of the truck initially plus the mass of the car, like that. Is that
Mhm.
clear so far? That's good.
Yes. Wait, so we're using the, I can't think of it. That's the really like long, intimidating one, kind of, right?
The equation,
Yes.
I'm using this one here, P equals
Okay.
mv.
Oh, okay. So you're
Is the,
just adding masses. Okay. Okay, that makes more sense.
I've done, this is P truck plus P car. Why? Because that's P initial. P truck, well, that's the momentum of the truck, right? M times V,
Mhm.
truck. Okay, you said that makes sense, but I just want to make sure. And then momentum of car, right?
Yes.
That's the total system. That's why this is so important to understand. What is PI equals PF? It's the system, not the car. The momentum of the car does not equal the momentum of the car later. That is not a true statement. It's the system. What's the system? The momentum of all the objects added together.
Yeah.
So then what's the final, right? And you can do the same thing. Well, it's the momentum of the truck, which is MV, M of the truck, and then truck final, we'll say. Sometimes you'll see a primed. Maybe let's use primed since we have more room. Does he use anything special to denote like final velocity and initial velocity?
Yeah, I think he does.
Because usually it's just VF, right? But you can't just say VF when you have two objects, because it's like, well, which object does this correspond to? So you have to be careful, and you got to have a subscript and another subscript, or a subscript and a prime, or a little something else.
Mhm.
But just let me know as soon as it's not clear, and we'll try to clarify. So then if I'm using primed, I can take that away. I don't care. Again, these are variables. I don't care what they're called as long as we know what they are. This is initial momentum of the system. This is the final momentum of the system. They have to be equal to one another. That's what conservation of momentum is. So what do they want out of all these variables? That guy. Yeah.
Yes.
So don't plug anything in. You solve for that first. I can go through the steps, but this is what it's going to be. Solve for what I circled in red. I think if I could do it, yeah. Plug in your numbers. I'll do it for it. I'll do it, but let me know if you're still with me.
Okay.
Initial velocity of the truck plus 25 times 20 minus 1325 times 28.5 equals divided by 2515. So great. I got a very reasonable answer. Makes me happy. 27.5 meters per second. Answer to the first part there. Is that good or no?
Yes.
Sure.
Yes.
So did that again. I mean, I was being a little careful here. You know, take your time and use all the skills you have, because everything you've learned up till now, like, it looks like a lot and it looks difficult, but it's the same thing. It's just a little more of what you've been doing. Draw your picture, understand direction matters, the vector, conservation of momentum, initial, final. And then what is the initial momentum of the two vehicle system? Oh, see, okay, wait a minute. He might have wanted you to use energy considerations here. let's just go through it, because I mean we got the answer. It is important to do what they want though. So the initial momentum, conservation of momentum. Well, this is everything I just said, basically. This is the initial situation. So we want the initial momentum of the two vehicle system. See those words there? It's the momentum of the system, truck plus car. Well, what is that? I mean, it's just this right here, right?
Yes.
I went a little too advanced, I think, because I think it can do a little simpler. That first part, at least you can find a little bit easier, but yeah, so initial momentum, but you're good, I think. So I'm going to just go ahead and that's what they want right here. They want us to find initial momentum. What is that? Well, it's the initial mass of the truck. It's the initial momentum of the truck, which is the mass times velocity, plus the initial momentum of the car, which is the mass of the car times the velocity of the car. Again, right, plug it in. It's going to be real quick here. It's 2515 times 32, because that's how fast the truck is moving at first, plus mass of the car is 1325 times 20. Great, we get a really large, crazy number. That's fine. These are cars. They're big compared to people in normal things, right? kg meters per second. Mass times velocity. Great. Was it conserved? I don't know. Let's find the momentum, the final momentum of the system. Well, what is that? Momentum of the truck, the final momentum of the truck. We'll call it primed to denote it's the speed later, plus the mass of the car, the momentum of the car, which is the mass times the velocity, the final velocity. Well, we calculated that truck momentum, 27.5. So 27.5 times the mass of the truck, all this stuff, 20 times 2515 plus 1325. They give us 28.5 as the final mass of the car. And we got a little bit different answer. I think that should have been 60 up here. But that's because I rounded these things, I think, because it's always conserved. Whether it's an elastic or an inelastic collision, it's always conserved. Momentum is, at least. That's one of the most important things in this whole thing. They're asking about momentum, right? Yeah, okay. Just I'm gonna look something up. Yeah, they're not talking about any of that. All right, so yeah, momentum is always conserved. So like I said, I rounded here somewhere, or maybe I actually made, okay, calculation minus MC, mass of the truck. Yeah, these numbers should be the same. I guess this is your homework. Should probably get the right work. Okay, let me just look at this real quick. Okay, since they said elastic collision, we know. So this is a good kind of trick for you. When it says, if you go up to the second sentence, assuming the collision is perfectly elastic, you say, hooray, what does that mean? That doesn't tell me anything. You say, no, it does tell me something. Kinetic energy is conserved. Okay. So the kinetic energy of the system. So what's the initial kinetic energy? Go back to your picture. The initial kinetic energy of the system. What's the kinetic energy of the truck plus the kinetic energy of the car? Just like the momentum thing. What's the, kinetic energy of the initial system, kinetic energy of the truck, which is this, plus the kinetic energy of the car. Makes sense? And then what's now I'm on the right side of the equation. What's the final kinetic energy? Well, the final kinetic energy of the truck, primed we like to use, but this thing is squared, plus the kinetic energy of the car, primed C squared. All these halves go away. It just makes things easier usually. And you would solve for the truck initially here, maybe, and you should get that. I mean, there's no way you get a different answer than 106,960 or whatever, 27.5.
Mhm.
Let's see though. Did you go through the calculation? I must have made an error somewhere.
I don't know. I got the same thing.
Yeah, okay. So I've solved for, did I? Divide this thing by MT. All right, so mass of the truck is 2515 times 32 squared plus 1325 times 20 squared minus 1325 times 28.5 squared. Different answer. 2515 square root of that. Okay, well, that makes sense to use the energy consideration. So, okay, sorry, write this one down for the homework then, because plug in your numbers. You're gonna get 28.4, which is awfully close to 27.5, and then when you do this, you'll get this, that's just enough, so you'll get the initial and final momentum the same. The key here is that perfectly elastic, obviously he wants you to use kinetic energy considerations or whatever. So remember that though, if it's inelastic, like elastic is like a billiard thing, a pool table. Have you played? Or you must know about that. And so, yeah, it just, there's no the contact is so short, it doesn't matter. And so we call that elastic, which means that the kinetic energy of the initial is equal to the kinetic energy of the final. But in an inelastic, it's not conserved. But momentum is always conserved no matter what.
Yeah.
So that's pretty good. And so you're good with that? I don't know, I can write it down if you want, but. And then kinetic energy only when it's elastic. Okay.
Okay.
Okay. Do you want me to go back? Do you want to write this stuff down? Are you good on it? Did you get it down?
I'm good. I've been following along.
Okay, cool. All right. So then number 2, what was that?
Oh, wait, sorry. Can you go back to the momentum part where it says momentum is conserved?
Yeah. Oh, this one, true. Yeah.
Okay.
And like, this is your math.
Okay.
And then just, you have to write this down, system, exclamation, underline. It doesn't mean anything if you don't remember this part. Okay.
Okay.
Okay. Good. All right, let's look at this. And so here you go. Here's a great example. This is good. He did this well. Because it says a bunch of stuff, cars, I don't care, crap, basically, until you see inelastic collision. Ah, great. Well, if it's inelastic, this is true, not equal. But this is always true. Everything, what I just said on the last slide, but now we have a problem, right? The two, and so you'll see this here. Okay. And I like to do this. Let me see if I can get a little tighter in here so we can get the equations on the same page. So initially, this is great. So a locomotive couples with a freight car that is parked on the tracks. locomotive coupled with a freight car that's parked on the tracks. So this time, check this out. This is the same situation, almost. So, okay, whatever, local. So this thing is moving at, 3. Fine. The car is not moving. V car equals 0. Stationary. So I won't put an arrow, I guess. So guess what happens afterwards? It's not like this, like it was before. I'll go back. This was the elastic collision, the elastic, where they're not connected. And so you'll see this in the inelastic where they're connected, okay? And so now all of a sudden, they're both moving together. They've stuck together. That's how we know it's an inelastic. It tells us that the two continue to roll down the tracks together off into the sunset. But when it's an inelastic collision, that's pretty much, usually it's like a Velcro cart or something, but
Yeah.
this is what it does. And then it gives you the final velocity. No, you're gonna have to find that. But now the equations look a little different, okay?
Mhm.
In this situation, we know we can't use kinetic energy considerations. Why? Because it's not equal, so it's not going to tell us anything. We've lost some of that energy to the friction when they got stuck. That's what's actually happening. Or so I'm told. I just realized I've never actually, went into a lab and looked at it, but it makes sense.
Yeah.
What is the velocity of the coupled cars after collision? Well, I don't know, but guess what? I know this. I know the momentum is conserved. Well, what is the initial momentum? I don't know, but I know it's the momentum of the locomotive plus the momentum of the car. What is that? Mass of the it's the momentum of the locomotive, m of the mass times velocity of the locomotive. And guess what? Let me use L. I don't know why I don't like those. It's like L plus the momentum of the car, 0. Why?
Because it's not moving.
Good. So hey, guess we're done there. Now, what's the final momentum? Maybe I want to see if you can tell me what this equation equals here.
Oh wait, okay. So to find the equation, you use the PI equals PF, right?
Mm-hmm. Yeah, we have PI here. So now tell me PF.
Oh, so is it just
It's all right. What is this in words? It's the final momentum of the system, right?
mhm.
So if we
So
want to find the momentum of the system, we have to add all the momenta together.
oh, okay. So M1 plus M2.
Yeah, well, careful. M it'd be momentum is M times V, so M1 times M V1, right?
Oh yeah. Okay. So M1 times V1.
So normally you'd be right, and it's okay. Don't get discouraged, but that is like generally you add up the momentum. Yeah, you're right. And then how many objects do you have? If you have 3, then it's this. But you got to be very careful here. In these inelastic situations, we only have one object, and convince yourself of that.
Yeah.
I know you can see it in the picture, but that's what the problem is too. They're connected. So now the equation is, well, it's the mass of the locomotive. Let me write this down. It's P equals mv, right?
Yeah.
What's the mass? Well, it's ml plus mc, right? I mean, that's the mass of that object right there.
Oh, okay. So you combine them.
Yeah, you combine them because they are one object now in these inelastic collisions. And that's what it says too. The two then continue to roll down the tracks together.
Okay.
So that's our m, and then of course we always have our v, and it's just vf because we don't know. And there's only one velocity, so I can just say v final. That's what they're looking for. That's the first part of this. What is the velocity of the coupled cars after the collision?
Okay. Oh, okay. So we're trying to find VF.
Yeah, that's the first thing we want to find. But we always know this is true. So that's why I always go to that first. When it's elastic, you probably want to go there first. That was a mistake I made last time. But we can't. We can't because it's not true this time.
Okay.
Now, I wrote these equations down. What do I do? conservation of momentum. This thing is equal to that. Why? Because that thing's equal to that, right?
Mhm.
Okay. So then I combine them. Again, I'll write it down. As I say it, I'm saying that. Oh, now I'm just going to substitute. Remember, I combine these masses because they are moving as one object at the end here. So then VF is simply the momentum of the locomotive initially. Those are terrible. Divided by the combined masses at the end. So I'm going to get 159,545 times the velocity, 3 divided by the sum of these masses. 159,545 plus 46,000. Any issues with this?
Wait, okay, so for the first equation, it's so it's VF equals ML MC.
The first equation is PI equals the initial momentum of the system. Remember, the car's not moving, so it's just the momentum of the locomotive. Is that, sorry, I was a little distracted, but I heard you say first equation.
Oh, so where it says like VF, is that ML VL?
Yes, yes.
Oh, okay.
Sorry. Yeah. Yeah, mass of the locomotive.
Okay.
And all I've done was combine those things. I solved for VF after I combined conservation of momentum.
Okay.
That's where that equation came from. Good.
Yes.
Okay, so it's kind of weird doing this because the velocity is the hard, like that. You solve the entire problem once you solve for the last velocity, because we've already have the initial momentum. That's the next thing they're asking, right? So what is the initial momentum? It is the momentum of the system, which means the momentum of the locomotive plus the momentum of the car. Well, what is that equal to? The mass of the locomotive times the velocity of the locomotive plus the momentum of the car, which is the mass of the car times the velocity of the car. But as you said, this is 0. Why? Because VC, the velocity of the car, is 0.
Mhm.
So then PI equals M, mass of the locomotive times velocity of the locomotive. Well, what does that do? You know, it's whatever it says. It's moving at 3, so it's 3 times its mass, which is 159,545. And then we solve for the final momentum, which is, like we said, it's the momentum of the system. But now there's only one object. What's the mass of that object? This.
Mhm.
Times whatever final velocity we got, right? Which same answer because we better get the same answer. It's different for some reason. So maybe you say momentum is not conserved because maybe he's trying to teach you that, because I said, all right, momentum, especially in your class, it is always conserved, but because that makes it easy to do the problems. But if you find this, so this is the possibility, because this is pretty easy. And like, as in, there's no way I screwed this up. And like I was saying, the momentum of the system. And so, well, if it's rolling down the, if a car is rolling down the road, you lose some energy to the ground, right? That's why you slow down if you stop accelerating, because you're losing energy to the ground. And some of that, Newton's law, it takes that energy. That's not Newton's law, but hopefully you see by now that energy and forces are closely related. And so, did he talk about this in the class about how energy? I know he talked about before about thermal and sound energy. So that's why it kind of makes sense here. But you just don't usually talk about that in a normal physics class. Did he mention that, how in these conservation of momentum problems?
Mentioned Newton's laws?
No, how energy is lost or momentum might not be conserved in these problems. Or did he did say that?
Yes.
Okay, so there you go. And so I guess the answer to that is momentum is not conserved in the end. And so you can always use this guy, but if you are losing momentum, then you also have to say the momentum of, it's such a weird thing. It's like the particles traveling, because you don't have momentum unless you have velocity, but the particles traveling from the vehicle to the rails, right? That attraction there. So normally, so if I solve for this equation, I'm getting a little too into it here, but, or this is the conservation of momentum. And so if you subtract both sides by PF, well, guess what you have there. But in general, you're going to have some extra energy because it's the momentum of the system. And so you want to include not only the momentum of the truck and the car, but also the momentum of those particles that are coming off the car. I'm just surprised that he's saying this to you, but if he did mention it, that's how you want to think about it. Okay. Hopefully this is all clear, though, because it is, I mean, it is fairly straightforward. And the most important ones are these collision things, inelastic collisions.
Yeah.
Okay. Cool. So those were those, that was those two. And that's it from that email. Do you want to go over either of these again?
Can we do a problem similar to these?
Yes, of course. Okay, so we'll just do it here. A car, 1,000 kg. It hits another car, moving at, let's give it a mass. Moving at, doesn't matter, 20 meters per second in an elastic collision. Okay, hits another car. Moving at, say it's a truck. And the winds up moving a bit faster because it transfers some of its energy.
Mhm.
Let's do 30. 20 is good. And then is moving at 28 meters per second. And then I will just go through with the same problems. How fast is the truck? Initial momentum, final momentum. This time, I would do initial momentum. Okay, sorry. He wants you to do elastic, so let's just do that, I guess. Okay, so we have an elastic collision. Bam. What does that mean? You tell me.
Okay, so because it's an elastic collision, it is Ki equals Kf.
Yes. And what do those mean? What do those stand for?
Initial and final
Initial, final, what?
velocity.
Kinetic energy.
Yes.
So, or in other words, and remember, it's the system. So, K, the kinetic energy of the car initially, and the kinetic energy of the truck initially equals the final. And we have equations for these. We always know in general that, this is why it's good to know about your subscripts and all these things. The primed I use for final sometimes. But that gives you, okay, 1/2 MC VC squared plus 1/2 MT. This is the initial. Does it help if I do this and like write what it is in words? Or are you following along?
If you can write it out, I think that's a little bit more helpful.
Okay, sure. Initial kinetic energy of car. And so is that, right? Initial, and I'm just going to write K E kinetic energy of truck. And that's there. And notice, of course, the subscripts, right?
Mm-hmm.
And then what is this thing equal to? Well, it's equal to that. So then we can say, okay, 1/2 MC VC prime squared, 1/2 MT VT prime squared. Where, of course, this is the final, this is the keywords, final KE of car. Maybe this is too much here. But of course, like I said, this equation, I just plugged in that for each of them. The kinetic energy for each one. Okay. And then you can say, because I'm going to want to solve here for, we want the final, it doesn't matter really. The truck we have, okay, so we have the truck, so we're going to want to find final velocity of the car, this guy. And so you have all this giant thing. Let's clean it up actually. So that'll be hopefully a little easier for you. So I'm just rewriting it after I canceled out the 1/2s. And then we want to solve again for the final velocity of the car. So If you want me to go through these steps, I will happily do that.
Yes, please.
Okay, sure. So let's subtract, MT VT from both sides. VT prime squared rather. And so you have MC VC squared plus MT VT squared minus MT VT prime squared equals MC, like that. This is just algebra, of course. Remember, we're just isolating that thing. So then we would divide both sides by MC, right? Those cancel, but we can then take the square roots to get rid of the square.
Mhm.
So when we simplify that, we would have this. And then you want to plug in your numbers from before.
Mhm.
But all this comes from kinetic energy is conserved. And then, of course, the equation for kinetic energy. Okay, so I've got the mass of the car times the velocity of the car squared. So mass of the car, 1,000 times 25 squared plus mass of the truck, 800 times 20 squared minus the mass of the truck, 800. And then the final, the primes are for the final. So it's minus the mass of the truck, 800 times, finally moving to 28. So 28 squared, great, divided by the mass of the car, which is 1,000. We take the square root of that and get a good number, 17.8. I don't think, I didn't write down the situation. Usually when I write a picture, it's the same exact one as that first problem we did though.
Mhm.
And yeah, this is the final velocity of the car at the end after the, after the car hit the truck, I believe.
Mhm.
So yeah, and then you would use, okay, now we want to find the initial momentum and then the final momentum of the system, right? And so, well, the initial momentum of our system, which is the car plus the truck, don't even have to use conservation of momentum right now. Well, I don't know, but it's the momentum of the truck plus the momentum of the car. It's plus all the momentums. But there's only two objects, so we know there's only two momentums. So then we say, oh, okay, it's this, the initial values here,
Mhm.
only the initial values. So then we can plug it in, and it would be, mass of the truck times velocity of the truck, which is, when it's initial, 800 times 20 plus mass of the car times velocity of the car is 1,000 times 25, 41,000 units of mass times velocity, of course. The same exact thing. What's the final
Mhm.
momentum of the system? Well, it's the final momentum of the truck, right? The prime is the final, plus the final momentum of the car.
Mhm.
Since the mass doesn't change, it's just mt times vt prime, the final velocity. Mass of the car doesn't change, final velocity. Of course, this just comes from with the proper subscripts. So mass of truck is 800 times 28. That's its final velocity. And then the mass of the car is 1,000. We calculated how fast it was moving here, 17.8. So we get 40,200, whatever. But the point is, it's not the same as the initial momentum because we have some momentum loss in the collision.
Mhm.
So no, momentum is not conserved, right?
Yeah. Okay.
All right. Okay, so that's good for this one. I know you got another one planned here. Did you have more worksheets or did you just want to continue working on some problems?
If we could just do more problems like this, it'd be
Yeah,
great.
sure.
I might have a worksheet. I'll look.
Okay. Yeah. Well, yeah, give me 10 minutes. I'm gonna get a break in, but then I'll meet you in the other room for Zoom.
Okay.
Okay, thanks. Bye.